Good evening, everyone. In this second part of the video, this simulation demonstration shows a frontal car scenario crash modeled using Abaqus, specifically leveraging the explicit solver for high-end impact analysis. Crash events are characterized by extremely short durations, typically in order of milliseconds, involving large deformations, non-linear material behavior, and complex contact interactions. So these factors make explicit dynamic analysis the preferred approach, as it avoids iterative equilibrium solving, and instead of using the solution through small stable time increments, that is what we say as quasi-static. So in this model, a vehicle structure or a simplified crash frame is assigned an initial velocity typically around 13.89 meters per second, equivalent to approximately 50 km per hour, impacting a rigid barrier. So the geometry is discretized using finite elements, predominantly shell elements for thin-walled structures. This allows efficient capture of bending and membrane behavior while maintaining computational feasibility for large-scale models. As material definition is critical in simulations, car crash simulations, the structural component are modeled using elastic material behavior with the isotropic hardening. If I were to be more specific, we are using elastic plastic material behavior with, as I said, isotropic hardening. Typically, steel properties include a Young's modulus of approximately 210 gigapascals and yield strength in the range of 220 megapascals, with the plastic deformation governing the energy absorption during impact, as it's already described in the Abaqus documentation if you are able to get it. Otherwise, I will just ping it in the description of this video. Under the crash loading, the material undergoes a significant plastic deformation, which plays a very critical role in dissipating kinetic energy. This energy is then absorbed using a mechanism which is very essential for designing effective crumple zones that reduce the force transmitted to occupants. So for this contact interaction, as we are defining using general contact algorithm, during the crash event, multiple surfaces come into contact simultaneously, including structural folding and self-contact. And the accurate contact enforcement, which is very essential to prevent numerical penetration and to ensure realistic load transfer. So the boundary condition, including the initial velocity of the vehicle model, while the barrier is modeled as the rigid body, which constrained degree of freedom. As you know, each solid body or a rigid body have 6 degrees of freedom. So the simulation time is typically set to a few milliseconds, sufficient to capture the full impact and the deformation process. And if I were to talk about Abaqus explicit solver, it very gently integrates the equation of motion using a central difference method. The time increment is governed by the smallest element dimension and the wave propagation speed within the material. So as a result, it is extremely helpful in managing the small time step, and it is very helpful in maintaining the numerical stability. So if we are using the Muni-Rivlin method for the impact analysis for the implicit solver, so the onset of impact, the stress wave propagate through the structure, requiring very fine time resolution. And as deformation progresses, the plasticity develops. These high frequency then affects the damped, or it allows slightly large increment without the loss of accuracy. So it depends upon us as an analyst that which model we are using for the crash simulation behavior. As a result of this simulation, it provides detailed insight into the crash behavior. Deformation plot shows a progressive collapse of the front structure, including how energy is absorbed through controlled plastic deformation. Energy plots are very particularly important in validating the simulation. Initially, the system processes kinetic energy due to the assigned velocity, as it directly changes the form of energy. So as a crash progresses, this kinetic energy is then converted into internal energy, as we study in the second law of Newton, primarily through the plastic work. So this study shows that a significant portion of the initial kinetic energy is dissipated within milliseconds of impact. Stress and strain contours highlighting critical regions where failure may initiate. These insights are used to, the reinforcement of structural component or redesigning geometry for improved crashworthiness. Now, talking about the crashworthiness simulation as demonstrated here, it is widely used in automotive engineering to evaluate structural integrity and occupant safety. So, our software Abaqus enables accurate prediction of deformation, failure modes, and energy dissipation under extreme loading condition, making it a tool used in modern vehicle development. It's an advanced simulation package which includes coupling and occupant modeling using co-simulation techniques, allowing the simultaneous evaluation of the vehicle response and the passenger safety system. Overall, this package highlights the capability that it is able to handle highly nonlinear transient problems with high fidelity. By enabling virtual crash testing, Indian engineers can optimize design, reduce reliance on physical prototyping, and significantly improve safety parameters or the safety performance parameters. In summary, it helps us evaluate the explicit crash simulation, which is not just about visualizing deformation, it is about understanding the physics of impact, energy transfer, and the structural response in a controlled and predictive environment. So if you are into the simulation of these vehicles or any explicit transient problems, if you are interested, if you are passionate about it, we can connect over the next videos I'll be uploading regarding the Abaqus simulation, and we can discuss it laterwards. Thank you so much for watching. Thank you.